Okay, so you guys at home missed out on the first two nomenclature. We're going to get started from number 3. What's our first step? We got to find the longest, the longest chain that includes our highest priority group, which in this case is the alcohol. So how are we going to number it? Left to right or right to left? Left to right. Perfect. Just like that, okay? So let's write our parent. Okay, and what's our prefix? Pentanol is the whole thing. So our alcohol is coming off from the number 1 carbon, 1 pentanol. That's our parent. Let's move forward to our subs. Okay, what are our substituents coming off? Coming off 5. We have this entire ether group, right? So we have to approach this using the complex naming, okay? So you always with the ethers as a substituent, you start numbering from the carbon that is directly attached to the oxygen. So this is our number 1, no matter what. Six, right? So we're gonna have to put hexoxy. Okay, and then when we're doing the complex naming for the substituents, we consider the substituent has like a pseudo-parent, and there are substituents coming off of that. So at our number 4, what do we have? 2 methyls, right? So we have 4, 4 dimethyl hexoxy. Put the entire thing in parentheses, okay? And then what do we have to include in front of that parentheses? 5 dash to indicate where it's coming off of our original parent, okay? Do we have to pay attention to any stereochemistry? No, perfect. So we can go ahead and write this in our box. It looks like I put a L right there. I hope this isn't gonna like erase everything. Okay, and then that would be our final answer for that. Any questions about nomenclature? Awesome. Okay, let's move forward to the facts. So place the following halides in order of increasing reactivity by SN1. Okay, so SN1, how many steps are in SN1?
2 steps.
2 steps. My boy Mustafa in the front. So we got 2 steps. Okay, so your intermediate, what are you forming? A carbocation, right? So what's the first thing that happens in SN1? Leaving group leaves, right? So we're going to get rid of that bromine, say it left, and we formed a carbocation intermediate for all of these. Like that. So in terms of the degree of our carbocation, which one would be the most stable? Tertiary, right? So let's go and compare what we have, right? So the first molecule, what we have secondary, right? What about the middle one? Secondary too. Okay, and what about the last one? Tertiary. So right away, so these are all positive charge on carbon, right? So which one is the most stable out of these right away we can say? The third one. So if this intermediate is the most stable, it means the original molecule was more reactive to form that intermediate. Okay, so now we have to compare and find the point of difference between the first option and the middle option. How are we going to do that? What do you guys think? Everyone said resonance. Perfect. So the first one has some resonance structure that you can draw. You can swing the pi bond onto that positive charge like a door hinge and displace the positive charge, right? So you can draw some resonance. Resonance does what to the molecule? stabilizes it, right? So this would be number 2, and this would be number 1. Okay? Any questions? Perfect. So let's move on to number 2. If a compound below will produce a Grignard reagent in good yield, place a Y in the box, and if it will not, place an N in the box, okay? So our Grignard reagent is very important for forming those carbon-carbon bonds, right? So is a Grignard reagent, is that a strong nucleophile or electrophile? Very, very strong nucleophile. So that's what you have to know. So a strong nucleophile, what's it going to react with? Something that is partially positive enough, right? So when we're trying to make the Grignard, we want to make sure that on that molecule or anywhere around that molecule, you do not have a partially positive or full positive charge for that Grignard to go and attack. Because if it goes and attacks, then you ruin your Grignard, right? So let's look at the first one and see what we have there. We have an alkyl halide, right? Specifically, this right here is the vinylic position where that bromine is. I'm going to zoom in a little bit for you guys. So on this molecule, would we be able to produce a Grignard in good yield? Is there a site on this molecule that is partially positive enough for a Grignard to attack? So there is a dipole moment between the bromine and the carbon, but it is not strong enough for a Grignard to come and attack it. So for that reason, we could use a molecule like this in order to produce a Grignard, right? What do you have to hit this with in order to produce a Grignard? What reagent you have to put on your arrow? Mg and ether, right? So if you put Mg and ether, your product is going to look, magnesium's your middleman. He goes right in between the alkyl chain and the bromine. So you would be able to do that with this. So you're going to say yes. Well, no. So for this one here, on the farthest right, it's a tertiary carbocation versus this one.
But this one is resonance stabilized.
Oh, can you get it onto the oxygen?
Yep. You forgot. See, when this is a BR, so once the BR leaves, it's going to become positively charged.
Yeah.
I think it's just not stabilized, right? If and the key has this, I think we just messed them up.
Wait, let me see. Oh, it depends. If we can get it into the oxygen, then you're right.
Because this one
go
is
here, positive charge. Mm-hmm. This would go here. So this is a secondary.
This one's not resonance stabilized even. It cannot resonate here, right?
The key, it's like that.
Mm-hmm. Because like this one cannot. So here, let me show you.
You can get okay. I'll clarify that. All right, guys, we need to go back to number 1, okay? So for number 1, the first option over here, right? When you do the resonance structure, yes, there is resonance. So when you do the resonance structure, you are able to get the positive charge all the way to the oxygen. And so when you get the positive charge all the way to the oxygen, it will fulfill the octet rule. And so for that reason, this one is actually the most stable. That was my bad, okay? Please forgive me. So, yeah. That's my bad. 3, 1, 2, yeah. So draw out the resonance structure for this first one right here, and then see how you'll get the positive charge onto the oxygen. And when that's the case, you fulfill the octet rule. Versus this right here is what's it called? Tertiary carbocation. However, you're not able to get it all the way onto the oxygen, so there is an atom in there that is not fulfilling the octet rule, right, in that particular resonance structure. That's very tricky. So does that make sense? Everyone's clear? Yes. So the resonance is going to stump that, okay? Oh. Here, I'm going to answer her, and then I'll get you, okay? Yes.
I was saying we focus on the resonance or on the octet first before we do the carbon.
Yeah, I would say look at the carbocations, see if they have resonance, if you can get it to resonate to the point that you get the positive charge onto the oxygen or even a nitrogen, where you're getting it to that all the atoms in that particular resonance structure fulfill the octet rule, then that would be more stable. Does that make sense? Yes, ma'am? You got it. Okay, and then I think in the hat, oh, she's good. Okay, so sorry about that, you guys. So let's move forward to number 2 and see what we have, okay? So if a compound below will produce a Grignard reagent in good yield, place Y in the box. So the middle reagent, what we have going on here, right? We have this ether, right? So what is the solvent we use in order to form a Grignard? Ether, right? So the whole reason why we use an ether is because the Grignard will not react with it. So for that reason, this middle compound would be yes. Okay, we literally use an ether in order to form the Grignard, right? So if we have an ether right there, then we're okay. The only exception to that rule is if the ether is 4-membered or less, right? Give a good example. Right here, right? A Grignard will most definitely react with the epoxide because these carbons are partially positive enough. Okay, so when you're trying to use Mg in ether to put your magnesium right in between that bromine and the alkyl chain, what happens is it will right away go and attack itself at one of these carbons, particularly the left one. Okay, so it's going to react with itself. You're going to ruin your Grignard, so you're not going to produce the Grignard in good yield. So we're going to put no. Sounds good? Any questions about that one? No? Yes, sure. About the epoxide? Yeah. So the 2 carbons that are involved in the epoxide are very, very partially positive. They're very reactive due to the ring strain and the fact that they're attached to that very electronegative atom at the top. Okay? So when you're trying to create a Grignard, which is a very, very strong nucleophile, it is going to go and react with one of those carbons, a part of the epoxide. So you will not be able to produce a Grignard in good yield because it's going to react with itself. Does that make sense? And if you have any more questions, the tutors, we have Danny and Faye going around, okay? Okay, so Dr. Bean told me today that UV spectroscopy will not be on this exam, so that is exciting news. So we're going to cross it out. So hopefully that gives us a little bit more time to talk about what will be on the exam, and that's Diels-alder reaction, okay? So place the following compounds in order of increasing reactivity with HBr, okay? 1 being the least, 3 being the most. So HBr, is that a strong acid or strong base? What is that? Strong acid, for sure. Okay, so we have a strong acid, and we're going to see if they're going to react with these guys, okay? So we have ethers being shown. We have an ether over here. We have an epoxide over here. And then we have another ether with these 2 benzene rings coming off of it, okay? So with an ether, ethers are not very reactive, right? And I'm not talking epoxide. I'm talking just a regular ether with enough carbons, straight chain. They are not very reactive. That's why the only reaction that we're learning in this unit to literally break them apart is high heat with acid, right? So HBr is something that will react with the ether, okay? But ethers are typically not very reactive. But if you put HBr with high temperature and in excess even, it will react with the ether. So that looks good so far. But let's move forward and see what else we have, okay? So in the middle, we have this epoxide, right? So with an epoxide, it's very reactive due to the ring strain, right? It's a 3-membered ring, very tight. It's not supposed to have this angle right here. So that's super reactive, right? And then over here, are we going to be able to have this acid react with this ether on the right? No, why not? Yeah, what about the benzene rings? Exactly. So what he said is it will not react because of those carbons there. They are sp2 hybridized, and so you cannot have this nucleophile. The nucleophile formed would be Br minus. Well, this won't react at all, right? But let's give an example, Br minus. So just like with SN2, this nucleophile cannot go and attack an sp2 hybridized site, okay? The unhybridized P just blocks the way, gets in the way for that Br minus. So this is the least reactive. So we're gonna put this as number 1, okay? Where's Danny, by the way? Danny, do you mind bringing me the key just in case so I can go side by side? I want to make sure we're confirming everything. Okay, so other than that, what's more reactive, an epoxide or an ether?
Is that your key?
No, that's 2018.
I have it on my phone. So
Thank you so much. The real MVP right here. Okay, so what's going to be more reactive, the epoxide or the ether? What do you guys think? Epoxide, definitely, because of that ring strain, okay? So in this mechanism, we have that oxygen, first step in acidic conditions, oxygen gets protonated, and then your weak nucleophile, or nucleophile, in this sense is Br minus, which actually isn't that weak, but it will go and attack one of those partially positive carbons that have now been activated, okay? Do you guys have any questions about that? Yes, that's a very, very good question. So with the epoxide, you see how these right here are sp3 hybridized carbons? So what degree do the sp3 hybridized carbons like to have? They like to have 109.5 angle degree. So here in this ring, like a triangle, they're very, very strained. They are not achieving that, okay? So that would be like 60 degrees. So that's way off. They're so strained. And in addition to that, there's a dipole moment between the oxygen and those carbons right there. So the electronegativity of the oxygen pulling on it, after you protonate it, the oxygen now gains a positive charge, and oxygen is extremely electronegative. So you're putting a full-on positive charge on an atom which is very electronegative. So that's very unstable. Does that make sense? Yes. Perfect. Okay. Let's move forward. So answer the following questions for the molecule below and place the answers in the appropriate boxes. What is the theoretically predicted multiplicity splitting patterns of the signal for proton A? So let's just answer the first one and then we'll read the others. So let's focus on proton A, which is right here. All right. So what contributes to the splitting pattern is always going to be, for the proton NMR, it's going to be your neighbor, not the carbon itself in those protons. The neighboring protons will split it, okay? So you look over to its neighbor and you do the n+1 rule. How many protons are on the neighbor of that carbon? 2. So you do 2 plus 1, and that gives you 3. So you write 3 in the box, 3 lines, or you can write triplet, up to you. Okay? Now let's do the next one. So what is the theoretically predicted multiplicity of the signal for proton B? So we are going to focus on now, let's do a different color. Proton B. So we can see that proton B has a lot of neighboring protons, right? So just by, if you were looking at the spectrum itself, you would see a lot more splits, okay? So we want to figure out theoretically how much there should be, okay? So let's look at the protons to the left of the protons B, okay? How many we have? 2. So we're going to do 2 plus 1, okay? Now, so let's check it out. Right here. We're getting to it. But you're doing excellent. That's very good. So, since she already spoiled it.
I'm sorry.
No, you're good. She's doing great. So right here we have 2. Let's just go and check the other groups, okay? And see if any of them are similar in environment. So if you were to look at the other branch coming off, the other CH2, CH3, like she said, they are the same environment, okay? So that means that they are going to participate in splitting in the same manner. So you group those guys together. So you did 2 plus 2 plus 1. So 4 plus 1, and that would give you 5. Is everyone clear about that? No? Yeah. So what I'm saying is, you see the protons that I pointed the arrows to? Would you agree that they're the same environment? Yeah, so there's both 2 ethyl groups, right? So they're the same environment protons, so they're going to participate in splitting in the same manner. You group them together within the n plus 1 rule. So that would be 1, 2, 3, 4, and you do 4 plus 1, and that gives you the 5. Perfect. So then we look to the other side. We have another CH2, but is that CH2 the same as the others? It's different. So what are we going to write? 2 plus 1, and that's 3. 3 times 5, 15. So we're going to put 15 lines. All right, so let's look at the next one. What is the theoretically predicted multiplicity of the signal for proton C? So where is proton C? Oh, this is a good one. So we have proton C, and it's involved in what functional group? What is it attached to? An alkene. So that's going to make a difference. You got to be really careful now. So you look at that proton itself, then you look at the neighboring carbons to that proton, right? And you ask yourself, how many protons do those have? So this neighbor, I'm going to highlight, I'm underlining it, okay? That has 2, right? So we're going to do 2 plus 1, okay? Now we look to the other carbon from the other side, okay? And we have this one right here has 2 protons. But are these protons of the same environment or not? No, why not? So they're locked into place, right? When you have these protons involved in the double bond, they're rigid. That pi bond is making it locked there. So there is no free rotation around the pi bond, okay? So because they're locked there and they can't freely rotate, this upper proton is in a different location than the bottom one. So we're going to say it's next to different things. So we're going to put 1 plus 1, and then we look at the other one, and that's going to be 1 plus 1. Perfect. So we're going to do 3 times 2 times 2. Okay? So 4 times 3. Does that make sense? Are we clear?
If the alkene was an alkane, would it still count as different environments? Or only it's an alkene?
Yeah. So she asked if the alkene was instead an alkane, would they count as different environments? And yes, they would. I mean, oh, no, they would not. Yeah, no, they would not. Sorry. They. I said it so surely too. They would not. They would be of the same environment because they are freely rotating rapidly, and so for the machine to detect it, they're going to detect them at it's just flipping so fast that it's not going to be able to detect that difference. Sorry? You mean if that was a CH3 group? So CH3 it would be 3 plus 1. And then 4 times whatever it is, 4 times 2. Well, it would happen to be the same. Very good catch, yeah. But yeah, definitely. CH2, those 2 protons on there would be of the same environment. The machine would not be able to detect them as different. So then, what is the multiplicity of the signal for carbon D in the proton-coupled C13 NMR, okay? So what is proton-coupled C13 NMR? Right, so now we're focusing on the carbon nuclei, and whenever it's under the conditions of proton-coupled, it means that the protons that are on that particular carbon of question are going to split the signal of the carbon, okay? So D, it looks like it's a little bit cut off. It's right there. Okay, so how many protons does that carbon have on it? 3, right? So we're going to do 3 plus 1. And that's going to give us 4. How do we feel? For HB, why did you do 4 plus 1? Let's look at HB. 4 plus 1? Oh, I see. Yeah, why did I do 4 plus 1? I guess I don't have it written down. Oh, it's the 5. Yes, so that's a very good question. And for those 2 ethyl groups that are coming off there, I wish I had my laser on this one. I can use this. These protons and these protons are of the same environment. You have to look at what they're connected to, right? So the ones on the top, that CH2, guys, you're being so loud. So if you want to talk, like, that's fine, but please keep it to a minimum, okay? Like, whisper, so that she can hear me and I can hear what she's saying. So for those right there, the CH2, the ones on the right, it's a CH3, right? And then going down, it's a CH. So if you compare it to the other CH2, it's the same things that are connected to it. And there's free rotation about those single bonds. Does that make sense? Okay. Any other questions? Mustafa.
What would the answer be if it said decoupled?
That's a very good question. So if the question said carbon D and proton decoupled, it would mean that all the signals would appear as singlets. Because decoupled, as the name is kind of insinuating, it means that the protons are not coupling it, right? So, or not coupling with that carbon. So every single carbon will appear as a singlet, regardless if it has 3 protons on it, or 1 proton on it, or no protons on it. Okay. Okay. So it'd be a singlet 1. Yes. So pay attention to that. If it says proton coupled. If it was another carbon that was the same. So with proton decoupled, it's always going to be a singlet. Because the thing is that only the protons on that carbon would split, right? If it's proton coupled. But in proton decoupled, they put it on a particular setting so that no matter if there's protons on that carbon, yeah, it would show up as a singlet, and you would never have a splitting pattern on any of them. Okay. Okay, Danny Helper, and then Emily as well, please. Just so, because I know I talk a little slower, so I want to be able to get through it all. So for reactions, let's get started. So what we have here is, what would you guys classify this as? What do you have on there? Di? Yes, perfect. So you have these 2 bromines in the vicinal position to one another, right? So when you have that and you have a strong base, sodium amide is what we have over here, right? What we're going to do is E2 reactions, but we're going to do it twice, okay? So sodium amide is a very, very strong base, okay? Here, we have protons, right? So we'll be able to undergo E2 twice. So what happens in E2, it's one step, right? So you're going to go here, push this down, push this off, and you form what functional group? An alkene, right? And then this base is so strong, it's going to happen one more time. So you're going to have that go and abstract this proton. This will come down, push off the bromine, and now we're going to get an alkyne, triple bond, okay? Now, when you have this very strong base, 150 degrees Celsius, what's able to happen is there's a base catalyzed rearrangement of that triple bond, okay? So is it going to stay internal or is it going to go to the end? What do y'all think? It's going to be terminal. Very good. So no matter where it's located in your molecule, we're going to move the triple bond all the way to the end of the molecule. We'll count 1, 2, 3 carbons coming off, right? So 1, 2, 3. We got that right. Are we going to keep it in its deprotonated form, or we're going to protonate that? Protonate it. Why'd you say that? Then H3O plus. If the then H3O plus was not there, it would stay in its deprotonated form, okay? Because of the sodium amide. Alrighty? So now what we have this mercuric ion, So H2SO4, H2SO4, and H2O. What do you guys think is going to happen now? We're going to form a ketone. Okay? You can use the Hg. What atom is that? Mercury, right? So that sounds like Merkovnikov, right? So you can use it to help you remember that your functional group, which is going to be a carbonyl, your functional group is going to go on the more substituted position. So all I'm going to do is write the 3 carbons out, okay? And then this is 1 carbon involved in the alkyne. They're analogous to this guy, these 2. And then in the more substituted one, it's going to gain the carbonyl, okay? And then the other carbon gains 2 hydrogens, right? So 2 hydrogens plus oxygen gives you water, right? So you're just hydrating this molecule, okay? Hydration of the alkynes. Markovnikov for that functional group. Now we have what is this called? Acetylide ion. Oh, I zoomed in. Let's make it better. Acetylide anion. Okay. Is this a strong nucleophile or strong electrophile? What do you guys think? It's a strong nucleophile. So where on this molecule is that going to go and attack? The carbonyl carbon that is partially positive. So this pi bond becomes lone pair, gives you O minus, and then you now have the attachment of that nucleophile. So we're going to write everything that we had before. And that's a CH3 group. And then now we have the attachment of that nucleophile. So the electrons that I circled are now the electrons that are forming that bond. So then we write everything else consistent. Triple bond to the carbon, all the way to the methyl. And then can I leave it like that or have to add something? Perfect. Because there is a then H3O plus step. So all that's going to do is it's going to protonate that oxygen, okay, and give you the alcohol, okay? If you guys have any questions about this, go for the tutors that are around. Ask the tutors. Okay, so then for number 2, we have an alcohol, and we have H2SO4 and heat. So this is that's a strong acid, right? Oh, I thought I heard something. So we have a strong acid. So this is acid catalyzed dehydration of an alcohol, okay? So dehydration means the removal of what? Water. So that's what's going to happen here. This guy's going to get protonated, and that's important for the mechanism section, okay? You'll see that a lot. And then that's going to leave as a leaving group. You're going to form water as a leaving group. That's very stable. And then we have 2 options of where we can form our double bond. We can either form the double bond here or here. Now, are these different in any way? No, right? Because it's symmetrical. So it doesn't matter which way you pick. And can we even form the double bond over here? Why not? There's no hydrogen there. You got to have a hydrogen, okay? No hydrogen there. That is an sp2 hybridized carbon that has a carbon, and a carbon attached. No hydrogen. You cannot put the double bond there. Carbon can't have that many. Okay? So let's put the double bond. Okay? So that's what we're going to get from that step. So we got 1, 2. Right? So we just want to make sure our carbons are consistent, right? We got 1, 2, 3 coming off, okay? So then, what's the substitution of that alkene? Disubstituted. Yeah. Okay, so when we hit it with MCPBA, what do you guys think is going to happen? Perfect. MCPBA. Okay, so in terms of our wedges and dashes, whatever is going down.
You're forgetting a message. What happened to the message?
I know, I haven't written it yet. Yeah, but good catch. I just want to make sure that we're going to put it on wedges and dashes correctly. So whatever is going up, let's put it up. H. But thank you, guys. Catch me if I miss anything. Okay, so I had the benzene ring shown as going down, and then I had also a hydrogen shown as going down. So I made sure to put them both on the same, like whether it's dash or wedge, I made sure to put them both on the same. And then I had the CH ring going up and another hydrogen going up. So I made sure to put them both, on a wedge, okay? And of course that can be interchangeable. Okay, and for this particular question, honestly, she did not originally give you the stereochemistry, so I don't think you would even get counted off for that. Okay, so let's look at number 3. What is that? Strong acid, strong base, strong acid, hydrochloric acid. So this is opening of the epoxide under acidic conditions. So what is the first thing that's going to happen under acidic conditions? Protonation of the oxygen, right? And then attacking the most subgroup. Perfect. So that guy would get protonated. This is like mechanism stuff, but I like to just show it, to make sure we don't make any mistakes. So we're going to protonate that oxygen, right? And then our weak nucleophile, actually, chloride, is going to come and attack one of those partially positive carbons that are involved in the epoxide. Which one is it going to go and attack? The A or B? A. Good job. So Dr. B knows BLAM now. Yeah, she said it in class. So happy. Okay, so for those that haven't heard it, B stands for basic. That means under basic conditions, the least substituted carbon involved in the epoxide is the one that gets attacked by the nucleophile. And under acidic conditions, the more substituted carbon involved in the epoxide gets attacked by the nucleophile. Okay? So we're going to show our Cl is getting attached to that carbon. Okay? And when it does so, it breaks the bond that's to the oxygen and props it open, okay? So we will put the Cl now attached at that A carbon, and now it's still gonna have the methyl, okay? That bond opened up, we still are attached to B. We have those 2 hydrogens, we're not gonna worry about it, but what we are gonna put is the protonated, okay? That alcohol that's protonated. Any questions about that? Opening of the epoxides are super important. Like even for the ACS exam, they love that stuff. So make sure you know it, okay? Ask if you're unsure. Okay, so now let's move on to number 3. And number 3, what functional group we have? An alkene, okay? And then we have BH3 complex with THF, H2O2, OH, okay? So what we have going on here, the alkene is going to react, and we're going to have hydration across our alkene. When I say hydration, just means you're adding the components of water across it, okay? But in what regiochemistry are we going to add them? Anti-mark. Yes. Very good. So you're going to add an anti-mark, or some people say non-mark, just so that you don't get confused with anti-stereochemistry, right? So, and as you're doing these, like if you can jot it down, it really helps. The repetition helps. Okay, so you're going to want to put that it was non-marked. And what about our stereochem? It's syn, right? So we have syn addition here. So we're adding an OH and an H across those carbons, and we are going to put the functional group, which is the OH, at the lesser substituted carbon. And which one is that? The right one. Okay. And then the other carbon is now going to gain the proton, and it's going syn in relation to the OH, the same direction. Okay? Perfect. So steps number 1 and 2 are combined. So on your arrow, you would put 1/2. Okay? You want to make sure to include those. You are not responsible for the mechanism for this. Okay? And then let's see what we have. Step number 3, we have elemental sodium, right? So what is that going to do to the alcohol? Yeah, you're going to pluck off that proton, right? Just saying, nah, you can't have those protons, right? Na, nah, you can't have it. So you're going to pluck it off and make an alkoxide, which looks like this. Right? Very basic. So you plug it off. So now, step number 4, what we got? So we have formed a strong base. We have formed a good nucleophile. And now, in our step number 4, what type of molecule we have? What's the classification? Alkyl halide. Perfect. So with alkyl halides, what are our 4 options with those big 4 reactions we learned in Orgo 1? SN1, SN2, E1, and E2, right? So you got to pick what's going to happen here, okay? What is the degree of that carbon with the leaving group? Primary, right? So which reaction it's going to undergo? No, hands down. SN2. Perfect, perfect. So this guy is going to come over here. How many steps? It's 1 step. Consider it all at the same time. It's going to attach the oxygen right at that carbon. So we can still show the stereochemistry. I think on her key, I don't think she shows it. Danny, do you mind unlocking your phone? Yeah. I want to see if she shows the stereochemistry on the key. I forgot. Can you set it?
Which reaction, number 3?
Number 3, does she show the stereochem? Okay, so on the key, she does not actually show the stereochem. So us doing that is just like us being good, but no points extra, I guess. But sometimes if she shows the stereochem, that's important. So that's going to go and attach itself. So I won't show the stereochemistry since that's not what the key shows. And then we now have that oxygen attached to this carbon over here, right? Just like that. So we have 1, 2, 3 carbons that should be coming off there. Let me make a bigger arrow. Okay, so that was just SN2, okay? Yes, ma'am. Sorry? I added an extra carbon. Let's see, so it really does look like it. Even when I was looking at it, I was like, it really does look like it. But let's check it out. So here we got 1, 2, 3, 4. 1, 2, 3, 4. And then that's bonded to the oxygen. And now the oxygen is going to, that lone pair is going to form that bond. And then that's going to be attached to this carbon, which is that carbon. And then, so that attaches right there. And then you form the bond. And then you actually go, wait, if anything, I think I left out a, no, I think I'm good.
You're good. It's that carbon is 1, 2, 3, and the bromination is 1, 2, 3, 2.
Yes, yeah. I'm good. You know, I just like to be sure. I don't want you guys to like see my answers and it's not correct and then, you know, I want to make sure we're right. Okay, so we are perfectly good. Let's move forward, guys. So we have HBr in excess and we have heat, right? So we talked about this. This is, you know, acid catalyzed cleavage of the ethers. We got this 5-membered ring over here. So we are in the reaction section. In the reaction section, you don't have to show the arrow pushing. So it's pretty simple what you got to do. You just got to, right, cut that. Cut this one right here. That's where it gets cleaved. You just change colors. Right, everything else the same, and now instead of having the oxygen attached there, that bond is now going to be whatever halogen is the nucleophile in there. So that's going to be a Br. Now it's going to be attached to Br, and then we go Br from right over there. Okay, you have the protonation of the oxygen. This forms your bromide. And then you basically form a good leaving group within your molecule. So what you want to pay attention to, and where she can really trick you on this one, is these carbons right here, okay? Make sure that they are not sp2 hybridized. If they are sp2 hybridized, is there going to be a reaction? No. Okay, so that's what you have to be careful for, the benzene rings and such. Okay, perfect. So now, step number 2, let's see. So looking at our reagent here, not what's on the arrow, what's right over here, okay? Looking at that, we have leaving groups, right? So the classification of that molecule is an alkyl halide, okay? So what are our degree of our alkyl halides? What degree are those? We got a 1, 2, we got a secondary, and then we also have a tertiary, okay? So then we look at our reagents, and we see that we have a methoxide, right? So is that going to act, you think, as a strong base or a strong nucleophile? What type of reaction you think is going to happen here? So whenever you have, so secondary and tertiary, secondary, you can't really rule anything out yet. Tertiary, you can rule out which reaction for sure. SN2, just throw it out, okay? But with the secondary, you gotta kind of pick here, and that's gonna be dependent upon what you have next to that number, what your reagent is. So we have methoxide, so that's a strong base, non-hindered, small, strong base. So that's going to take E2 preferably, right? The only time it would take the SN2 route is when? If your alkyl halide is primary. So we're gonna do E2, and we're gonna do it twice. Notice, this is your little hint. You have excess there. So it's going to happen at 2 different sites on the molecule, okay? So we'll show it happening right here. So we basically have hydrogens here, right? Hydrogen here, okay? And we're going to, how many steps does E2 happen in? 1 step, very good. So we're gonna have our base come and pluck off these hydrogens, push the bond down, push off our leaving group, and we're gonna form double bonds, okay? So where do we form the double bonds? Is it gonna go, for the first one, is it gonna go here, or is it gonna go here? What do you guys think? The one that gives you your more stable product, the one that's giving you the more substituted product, right? Your alkene. So that's gonna be the one that goes to the right, okay? Because to the right, it's going to be 1, 2 di-substituted, but to the left, it would be mono-substituted. You guys see the difference there? Yes? Oh, Danny, your phone is low. I have one if he doesn't have one. Ooh. Perfect. My savior.
No, you're her savior.
No, I'm not. Y'all are doing good. Okay, so let's see let me make sure we got all the carbons indicated. So we got a 1, 2, 3, 4, 5, 6, 7. So we got 1, 2, 3, 4, 5, 6, 7. Okay, so we're gonna want to make sure that this 1, 2, 3, 4, 5, 6, 7, 8. Okay, perfect. So we got our set, our the right number of carbons there. I accidentally put this one as a carbon. Okay, so now what we formed is a conjugated diene. You see that? And conjugated dienes are going to react in a particular way. Okay, so normally when you have an alkene and you hit it with HBr, for example, what are you going to get? H on 1, bromine on 1, right? Preferably the bromine on the more substituted. All right, but here with these conjugated systems, we get something a little bit different. Let's see with H3O plus what's going to happen, okay? So we have these two double bonds, right? So let's just go ahead and pick one of them to react, okay? We're gonna have to show it with both of them reacting, so this takes a while, but this double bond is gonna get protonated, okay? So let's show the intermediate that happens here, right? And this would be like 4 points on your exam, so you're gonna wanna put these brackets like that, and you show that double bond went and attacked, gained a proton. Okay, draw it consistent. Now the pi bond is gone, and now your positive charge is going to go to the carbon that is closer to that other double bond, and the other carbon is the one that gains the proton. Okay, that is one intermediate. Now let's show the resonance for these intermediates. Okay, so we have a carbocation. We can move this over, swing it like a door hinge, and displace the positive charge onto the carbon that's over it, next to it. Double bond moves to over here, and then we displace the positive charge onto this carbon. Does that make sense so far? We're okay so far? Good. We have these two options. So remember, with resonance, it really truly looks like the hybrid between the two, right? You're not going to isolate either one of these. It has a character from both. So with the first intermediate, we have a secondary carbon, right? Secondary carbocation. Okay. And with the other one, what do we have? Also secondary, right? So we are basically delocalizing this charge between two secondary carbons. Now let's give the hypothetical reasoning. Let's say the other double bond went and attacked, okay? Went and attacked this acidic proton over there. Let's show the intermediates for that and the resonance structure. So we draw it as is. Keep the other double bond as it was. And now remember, the positive charge is going to go to the one that is adjacent to that double bond in order for us to show that resonance structure, okay? Not to the other one, regardless if the other one is more substituted. Okay? So now what we have to show the resonance contributor for this one. Okay, so we're going to swing that one. Boom. Displace the double bond to right there, and now the positive charge goes onto this carbon. Okay, now let's look at the degree of these resonance structures in the carbocations. So the first one was the degree. Secondary, right? And then the one on the right, what's the degree? Tertiary. So that's the only one out of these guys that's tertiary. So now let's pay close attention, okay? What we have here, right, the conjugated system is not symmetrical. So it really makes a difference which double bond you're using to go and attack, okay? So the intermediate at the bottom, that's shown in those brackets at the bottom, right, you're displacing the positive charge between a secondary and a tertiary carbon, right? So right away, this intermediate is not going to form. It's not going to be able to be isolated as much as the other because the other one is more stable. You're displacing the charge between secondary and tertiary as opposed to secondary and secondary. So we cross out the top one and focus in just on the bottom one, okay? Now, let's go to our number 3 and see what's rated on the arrow. So what she's gonna give you a temperature. She's gonna give you what's considered a low temperature, which could be 0. She could give you a high temp, which could be 50, 40, something like that, okay? So here, what do we have? High temperature, right? So if we have a high temperature, right, that means that enough of these molecules have enough energy in order to get up the bigger hump of activation energy in order to give you the more desirable or the more favorable product, right? And the favorable product is the more substituted double bond, okay? So what we drew here is the intermediates, right? But which one has the more substituted double bond? The secondary one, the one that has the less stable transition state, right? So the reason why we draw this out is to show what the transition state's gonna look like, right? So they said it perfect. The one on the left gives you the more substituted alkene once you have the attachment of the water. Water as a nucleophile. It's gonna come, it's going to attack, and attach itself right there. And what happens next is that deprotonation, okay? So this would be your product like that, and the attachment of the OH goes to this particular carbon, even though the transition state is less stable, but because you have a high enough heat, you are able to surpass that point, okay? So that one's kind of tough. That's the answer. So do you guys have any questions? Yes. Why did I cross it out? That's really good. So she asked why I crossed it out. So what we're trying to show here, we're trying to show the intermediate, right? As you form that positive charge, then we're showing the 2 resonance structures, right? The first intermediate is not as stable. The top one is not as stable because you are displacing that positive charge from a secondary carbon to another secondary carbon, versus the bottom ones, you are displacing it, delocalizing the positive charge between a secondary and a tertiary. So the top one just doesn't have a chance to be formed yet, okay? If you have a symmetrical system, you don't have to write this out, okay? You just do it for 2. You don't have to do all 4, okay? Good question, okay? And if you have any more questions, please ask the tutors for that one. Let's do this. So we have Layla. We have lithium aluminum hydride, right? So our friend Layla, she's psycho. So she's gonna go and reduce everybody. Everyone in her path, she's gonna just reduce it. So all the carbonyls, like all the esters, ketones, aldehydes, gonna reduce it. So this lithium aluminum hydride is supplying a source of hydride, particularly 4, right? And it's going to be able to react twice. Boop, to do the short mechanism, right? Because we're in reactions. That's what's going to happen. You attack it with the hydride, comes back onto the oxygen, comes back, reforms, pushes off the leaving group, and then another hydride would attack again, okay? But what is important in the reaction section for you guys to show is just what you end up with. So you're gonna end with that. You have the carbon right there. That was the carbon of the carbonyl. And now it has been reduced all the way to a primary alcohol. Okay? Any questions about that? Sorry? Yeah, so with an ester, that oxygen is able, I wouldn't call it stable, but it's a good enough leaving group in order to come back down, kick it off. Okay? So that's what you would get for the first step. Now let's use PCC. So PCC, what type of agent is it? Oxidizing, perfect. So what you're gonna do is you're gonna write the same number of carbons that you have, right, just 1, and you're gonna oxidize it. Are you gonna oxidize it to an aldehyde or to a carboxylic acid? Aldehyde. Perfect. All right, because PCC is not as strong. What oxidizing agent is stronger? Jones, perfect. Yes, sir. So then What do we have on our number 3? What type of reagent? Grignard, famous Grignard. So Grignard, gonna come and attack. Pi bond becomes lone pair, and you have the attachment now of that carbon group. So we draw everything from the left the same, right? You formed an O minus there. Now you have the attachment of the entire benzene ring. And then, of course, we still had that hydrogen there, so you can show that. You got to show that. And then, what am I missing? Perfect. You have then H3O plus. The then is very important. And we're going to protonate it, okay? Sounds good? All right, this is a new one, okay? This is what Dr. Bean talked about today in class. You might have gone a little fast, so I'm going to try to break it down. There's a lot of things you got to consider. It's not too bad as long as you practice several of them. You have to think about the stereochemistry of this reaction. You got to think about the regio. Oh, it just got so cold in here. It's just me. My goodness. What the heck? So we got to consider the stereochem, and we got to consider the regiochem. And yeah, that's pretty much it. So this is called, what is this called? What type of reaction is this? Diels-alder. How do you guys feel about Diels-alder, just so I know? Okay? You feel okay? Okay. So with Diels-alder, what you're going to form is typically a cyclohexene ring. So you're going to form a 6-membered ring. Okay, it has this common structure. You have 2 parts. You have what is called a diene, and then you have what is called a dienophile. So of course the dienophile likes the diene, right? So you have to have both these pairs, okay, to happen. And the diene, as the name tells you, right, you're gonna have 2 double bonds conjugated to one another. Miriam's here. Azizam. So, does anyone speak Farsi? Do you know what Azizam means? Yes. So, she's my Azizam. So, this right here is your dienophile, okay? And what this happens is a concerted mechanism, all at the same time. That goes there, this comes down. Do you guys see how the 6-membered ring is coming about? I wish I had my laser, but you have the 6-membered ring, okay? And that's the general backbone structure of it, okay? So you just gotta look for that in the molecules that we're being given now, okay? You gotta make sure that your diene, it has to have what conformation? S-cis. And S-cis means that about the single bond, you have the double bonds going to the same direction, okay? That's what S-cis stands for, okay? You'll see that in facts. Now, on your diene, right, the diene approaches the dienophile, right? Dienophile approaches from the underside, and then your diene has to be more electron rich. So what does it want to have attached to it? Electron donating groups, okay? So you'll see maybe in the notes she'll put E, that's electron withdrawing, she'll put E, DG, or she'll put D, something to indicate that you have electron donating groups, okay? And electron donating groups are going to, like the name tells you, donate electron density. For example, like this OCH3 and the other OCH3, which donate via what phenomenon? Resonance, right? That would come down, push that onto the carbon. So you're making that carbon a little bit more negative. Right? And that's what you want. You want it to be more nucleophilic. Okay, so that's talking about the diene. Now your dienophile, opposite trend, right? So your dienophile wants to be more partially positive. So what type of groups do you want to have on there? Electron withdrawing. Perfect. So electron withdrawing groups, can you guys name some examples for us? Yeah, and what's something in common about an aldehyde and a ketone? Yeah, so you have this carbon which is partially positive now, right? You can show even a resonance structure. Doesn't contribute much, but you can put a positive charge onto those carbons. So whenever you have something like that directly attached, an ester like in this example, whenever you have something like that directly attached, that is going to be withdrawing electron density, okay? So let's place our dienophile in the same kind of, I like to put the double bond vertically, right? Just like in our example previously, so you guys can see it better. Like that. Okay, so I just literally rotated on the paper so you can see it side by side, the diene, okay? And then what we're gonna have, concerted mechanism, you go like this, you go like this, and then this, where does that go down? Comes down, okay? So you're gonna be forming a double bond of some sort, right? So in your box, let's go ahead and put the 6-membered ring. And now we have formed a double bond right there, okay? So the bond, I will highlight for you guys the bonds that are getting formed, right? So we have formed this bond. That's a really big highlighter. Those are the two bonds that have now gotten formed. So those are the ones that are the dotted lines, okay? And then, of course, the number 1 carbon and 2 carbon of our dienophile are going to be 1 and 2 right there, okay? And then our carbons right here. So from our diene, we will number our diene. So that's 1 and 2 right there. 1 and 2 right there, okay? So from our number 1 carbon, what do we have coming off? The OCH3, right? From our number 2, we don't have anything coming off. Well, now I have 2 number 2s, but of our diene, okay? Now we have to pay close attention to, firstly, we have to pay attention to where we are going to put that dienophile, okay, the electron withdrawing group. It has to be, if you were to count around the ring, it has to be 1, 2 or 1, 4. Okay, away from the donating group. So you look at this, let's say, I'm gonna get rid of these numbers so we don't get confused. And change this. We got 1, 2, 3, 4, right? We're counting all the way around the ring, right? So at our number 4, we want it to be 1, 4 or 1, 2. So, and when I say it, I mean the electron withdrawing group. So we are going to get our electron withdrawing group, which is particularly the carbonyl. We are going to put it directly here. Okay, you have to put the carbonyl coming off of the number 4 carbon. If you had put it coming off of the 5 carbon, then what would you get? You would get 1, 3, right? And that is not going to give you the most stable transition state, okay? So you got to pay attention to that. Now, in terms of stereochemistry, you want your electron withdrawing group to always be coming from the endo position. That is more favorable. The endo position just means that it is going down in the space from the ring, okay? It approaches from the bottom side. So that means that to show that, right, I could put a dash going in between the number 4 carbon and the carbonyl, but rather, just for drawing's sake, I will put the hydrogen there going up, so that implies that the carbonyl is going down, okay? And then the other one, let me also put it going up, and then we'll finish it, and then I'll answer your question. So we still have to consider the number 3 and the number, the number 3, which is that carbon right there, with the OCH3 coming off. So where are we going to put that in the space? Up or down? Like wedge or dash? Wedge. Why'd you guys say wedge? So it's going in towards the space of the diene. Whenever it's going in towards that pocket, you have to imagine that you're putting your hand right there and you're pulling it upwards, okay? Like dienophile comes here, diene is here, and it pushes it up. So whatever is facing towards the middle is going to be pulled up in the space, and whatever, of course, is going towards the outside has to go down. So we'll put the OCH3 on the wedge on number 3, okay? So that's what you would put in your box, but let me answer your question. The hydrogen? Yeah, I think I would put it as dashes for the dienophile attaching. I would just put the endo position as dashes, and I would put the hydrogen on wedge. But I think if you just put it on dash, it should be okay. But if you want to be like extra sure, like just to make sure like they're not gonna take off anything from you, like you can put them on wedge. But it should be fine. Like it's just for those with the ring shape.
It's about to die.
Yes. The OCH3 on the wedge, 100%. And I wish I could like show you guys in a way, but it's up there. So basically, whatever is going towards the inside, I'll highlight it. So when I say going towards the inside, I mean like that OCH3. So if you were to look at other examples, for example, you would have an H going up like that. You see it? So the H is going outside of that diene, and the OCH3 is going inside of the diene, and whatever is going inside is going to flip upwards, and whatever is attached to that carbon has to flip down. So that's what's going on there. In towards the diene, perfect. So if you had this structure, for example, what's up? There is one, but it's for your phone, but I think your phone is good.
Is there two?
Oh, look, there's two. So imagine you have this structure. Oops. Like that. This is the prime example of this, okay? So when that diene is approaching the dienophile, you can think that this like connection between those two carbons, the bridge, is kind of flipping upwards like that. So it always goes up, and that's when you're gonna see those bicyclic compounds with that thing going up in the space. Yeah. So just remember, with this, it pushes it up. So whenever you have any groups, even if they're not connected, like the OCH3, whenever you have any of those, it's gonna go up in the space. Okay, do you guys have any questions about Diels-alder? Okay. Okay, let's do mechanism. Okay, mechanism. So let's see, we're gonna have to show one step at a time, show all of the intermediates and all of the formal charges, and we don't need to show transition states, of course. When you're doing the mechanism, I highly recommend for you guys to compare your reactant to your product and identify what is different between the two, okay? That will give you a plan. So what do you guys see? I see, yeah, a ring expansion. So the molecule on the left has a 5-membered ring versus the molecule on the right is 6-membered, right? So there's a ring expansion. I also see that this OH group has been removed, right? So maybe it left as water. Somehow it has to go somewhere. And what else do you guys see? Alkyne, is that what you said? Yes, perfect. So now we have the introduction of another double bond, right? Guys, can you lower your voice just a little bit, please? Like, it's really hard, I think, for me to even hear him talking to me. So, like, it's okay to talk, but, like, please just keep it down, okay? So that's what we got to identify. Then we have to identify our nucleophilic sites and our electrophilic sites, okay? So what are our nucleophilic sites on our reactant? We have the double bond, and we have the hydroxy group, the oxygen. And then what about electrophilic sites in general on the arrow? Perfect. So we have the sulfuric acid, so there's a partial positive charge on the proton right there. And so now, of course, nucleophile likes to attack electrophile, so now we got to decide, is our double bond going to go and attack that partial positive hydrogen, or is it our oxygen? Why'd you pick oxygen? It felt right. It just felt right. You're so right. It's going to be the oxygen. And the reason why I would go for that is just because I don't see it in my product. Like, where the hell did it go? right? So it must have reacted, must have formed water as a good leaving group and gotten out of there, right? Also, you see in your product, you see two double bonds, right? So I highly doubt she's gonna make you guys form it twice. I mean, I don't know, but the chances are smaller. So I would just go with the oxygen and see if it works. If it doesn't, then we go back. Okay, so we write everything else the same. Like that. And now we introduce the proton. So what charge goes on that oxygen? Perfect. So we formed what as a good leaving group? Water. So what is water going to do? So it's going to leave. And what type of carbocation are we going to form when that leaves? Secondary, right? So that's perfect. We don't got to do a hydride shift. I don't even know what you said. We don't have to do a hydride shift or anything. If it was primary, we got to do it at the same time. Okay? And remember our alkene. So, like that. Yes. So she asked if it was primary, do you have to do the hydride shift in the same step at the same time? 100%. You have to do it. That's like pushes it off the ledge, basically, in order to get it to a secondary carbocation. Primary is too unstable. So water left, and we got a secondary carbocation. Perfect, perfect. So now let's compare this to our product, right? In our product, we see a 6-membered ring, and I want you guys to even use these alkyl groups that come off of the ring to help you guys out, okay? So I see like this isopropyl and a methyl group. I see the isopropyl, right? But just looking at what I have right now, the carbocation, I don't yet see that isopropyl. So in some way, shape, or form, I have to form that isopropyl at some point. And at the same time, I have to expand the ring. But how many carbons do I want in my product? 6. How many I have right now? 5. So I have to expand it by 1 carbon, right? So if I were going to try to expand this, let's put it in red. If I were going to try to expand it to this carbon, right, that would be 6, right? If I were going to try to expand it to the one that currently has the positive charge, what would be the size of the ring? 7. So we got to move the positive charge. Methyl shift. Perfect. You said it. So we're going to do a methyl shift because we want to form a 6-membered ring, not a 7-membered ring, and we want that isopropyl. So let's do the methyl shift, displace the positive charge. And you can write methyl shift or alkyl shift on your arrow if you want to. Sorry? Nope. It's able to move. The reason why, it's energetically favorable, right? So if you move that methyl group, what degree carbon are you going to put that carbocation on, that positive charge? You're going to put on a tertiary, which is more stable than secondary, right? So perfect, perfect. So we moved the methyl, and now the red carbon gains what? A positive charge. You see that? We're all good? Okay, so then what we want to do, we want to form that 6-membered ring that we see in our product, right? So now what can we do? Ring. Yes. So I say, I will number this for you. Maybe that will help. Do you guys want me to number it? Four. Perfect. So which bond is the one that has to move? Between 4 and 5. So let's see. If we were to move this to where that positive charge is, we would now displace the positive charge into the ring, and then we would be forming the ring with the isopropyl coming off and that 8-numbered carbon coming off as well. So if we do that, I now know that it's going to be 6-carbon rings. So I'm just going to write a 6-carbon ring and not get too caught up with how it looks, I'm gonna write the 6 carbon ring and then go back and number and make sure everything's good. I like to keep it consistent with the product. So like, for example, if I see that, let's put it red. So the number 7 carbon, the one that has the positive charge, is the one that has to be this guy, right? Because that's the one that has, I wrote it in the product. So that's the one that has the isopropyl, and it also has the methyl group, right? So I'm gonna just put this as my 7, okay? And then I look at my numbering, right? So right here, 7 is going to have what coming off? Isopropyl, right? And then it's also going to have that methyl group, the carbon number 8, okay? Like that. Okay, and then in addition to that, let's see what else. So we have the carbon number 7 now formed a bond with 5, right? So carbon number 7 formed a bond with 5. So we're going to put in our red pen 5, okay? And then let's see what else we have. So coming off of the other side of number 7 has what carbon? 4? Are you sure? Yeah, it's 4. Yeah, number 7 from the other side is going to have 4. And then what else does 4 have coming off of it? A methyl, which is 6. Perfect. So that's our methyl, which is 6. And then also connected to 4 from the other side, what do we have? 3. Well, I should have put that in red. Sorry. 3. And then also coming from 3, what do we have? 2. Coming from 2, we have 1. So now we've kind of connected these guys. And we want to make sure that we have that double bond still between 3 and 2. Right? Nothing happened to that, so we're going to keep that consistent. And now, remember, we had a positive charge. So now, which atom is going to gain the positive charge? Number 3, not quite. Number 4, right? Number 4 lost the bond with 5, so now number 4 is going to gain a positive charge right there, okay? So let's look and compare to our product. So it looks pretty similar, but what's the problem? Can y'all see it? The double bond, right? We only have 1, we gotta have 2, and also it's in the wrong location. So what can we do? How can we move pi electrons? Resonance? My guy. So we have resonance, we're gonna move that up. So let's put this double-headed arrows. We form the double bond over here. Which carbon gains the positive? 2. Perfect. And I made sure that we got everything else that was there, right? Okay. And now what's different between these two? The double bond, right? So remember, we have a proton right here, right? So what can we use in order to pluck off that proton from the double bond? Yeah. I mean, you formed water as your leaving group, so you could have used water too, but let's just use the conjugate base just for fun. So you would write it in this form, basically, and you would go and deprotonate that proton right here, form a double bond, like that, and that would give you to your product. So what type of reaction was that at the end? With the carbocation intermediate, base, deprotonates, E1, perfect. Any questions about that? We're good? If you have any individual questions, be sure to ask the tutors walking around. Yes, ma'am. Sure. Is that good? Take your pictures. Okay, so we'll do synthesis. Let's read what we can start off with. So we can start off with a cyclohexane. Cyclohexane, just like that, any alcohols, alkenes or alkynes, so no alkanes, of 3 carbons or less. So less than or equal to 3 carbons. And then let's write the different kinds we can have. So we can have alcohol, 1, 2, 3, with an OH like that, right? And then we can have alkene, 1, 2, 3. That was a bad alkene. Okay, and then we can have alkyne. 1, 2, 3, right? So that's our starting materials. We want to make sure that we don't go back to an alkane because that would dock us off points. So now when we're doing synthesis, I would really recommend to just look at what functional groups that you have on your molecule. So what functional groups do we have here? Alcohol, perfect. Alkene, that's all that I see, right? Cyclohexane isn't gonna do much. That's an alkane. So what that means that those were involved in the previous step at some point, right? So those are things that are reactive. Those are things that we could have formed. So for me, when I look at the alkene and she puts those 2 hydrogens like so big for some reason, that's giving you a hint, okay? That she's putting them particularly in this cis conformation, right? So what do you guys think we could have gone back to, use a particular reagent in order to get an alkene in the cis conformation? What? Sorry? NaNH3, you're close. That would give you trans. What's the other guy? Lindlar's catalyst. There you go. And H2. Is that what you said? Sorry, I didn't hear you. Yeah, so H2 and Lindlar's catalyst takes us back to what functional group should we have had before that? Yeah, so we're just going to write everything analogous. 1, 2, 3, 4, 5. And then that is going to be attached to One, 2, 3, 4. 1, 2, 3, 4, and that's going to be attached directly to the benzene or the cyclone. That's going to attach. Okay, 1, 2, 3, 4, directly attached to the carbon that has the alcohol. Okay. So, what do you guys see? What functional group we have now? We still have the alkyne, and we have an alcohol. And you notice how this right here, wait 1 second. Yeah. I think so. 1, 2, 3, 4, and 4. 1, 2, 3, 4. No, I don't. I don't. Okay, so because we have 4 groups coming off of our product, like 4 carbons, right? And that's how many we have in the original thing. So we're good. But yeah, perfect. So whenever you see a triple bond very close to an alcohol, you're going to use the acetylide anion to go and attack some electrophilic site. So you got to pick, is it going to be a carbonyl or is it going to be an epoxide? What do you guys think? Let's pay attention to where that alcohol is and where the group is attached, okay? This is your alpha carbon, right? The one directly attached to the OH. And then you go down 1, and that's your beta carbon. So you guys see how that alkyne, that acetylide anion must have gone and attacked at that beta carbon, must have formed this bond right here. So that's why we're going to go with epoxide opening, okay? So you see a beta substituted alcohol, right away you got to think epoxide opening, okay? Whether that be acidic or basic conditions. So let's write this down. Let's write down the epoxide first. Like that. And then those 2 carbons that are involved in the epoxide, the alpha and the beta, just like that, okay? And then we have a nucleophile that must have come and attacked the lesser substituted side of that epoxide. So let's put our other piece. We put plus, and then we write the acetylide anion. Like that. Okay, so that must have come and attacked. So what conditions we have? Remember, acidic or basic? Basic. So what side should it go and attack? The lesser substituted side. So that means that it's going to go and attack this side. Is that what we see in our product? If your answer is yes, then you're doing it correct. Then this bond would have broken, formed what charge on the oxygen? So what do we have to put on the arrow? Then, the word then is so important. Then H3O plus. Okay? So then let's form the acetylide anion first. Well, it says we can start with alkyne, so that's nice. So all we got to do is figure out what we use to deprotonate it, right? The alkyne. So what can we use? What's a strong enough? Yes, sodium amide. Right? So this is a strong enough base in order to go and deprotonate this slightly acidic proton right over there. You're awesome. Oh, you gotta go. Thank you so much. Oh, your laptop?
Yeah, it's my laptop. Thank you.
Text me the key right now so that I can send it to the people after. And you're good. Take your computer.
No, you can keep it.
Are you sure?
Because I have to take my iPad. I'll meet you after.
Okay, خلاص. I mean, I don't know if you need your laptop though. It's like I'm taking everything from Danny. Like, I'm like taking all his belongings. Okay. What? I have one. It's okay. But okay. So now we have to ask ourselves, how do we form the epoxide? Perfect. Right? So what was our functional group before that? Alkyne, perfect. So the carbons that now involve the epoxide must have been involved in the alkene. Okay? We hit it with MCPBA, that gives you the epoxide. Now we have to ask ourselves, how are we going to form an alkene like that? So let's try H2SO4. Let's see how it's gonna go. The only thing is I see a terminal alkene. So, but let's say we had the alcohol before, right? We're gonna go with H2SO4 because I know a lot of students are gonna ask about this, okay? So where did you wanna put the OH group with H2SO4? On the ends? You wanted to put it here maybe? So if you were to do H2SO4 and heat on this alcohol, remember you have a primary alcohol. So what's the problem here? The problem here is that the carbocation is going to be on a primary carbon, so there's going to be a rearrangement, right? So you're actually not going to get that as your product. You're going to get the double bond in here. Okay, it's going to rearrange. So we want to avoid doing the primary alcohols with the H2SO4, right? If we put, let's say we put the alcohol, let's say we put it here, okay? And we do H2SO4. Are we going to get that as our major product? So what I'm asking is basically, we have this alcohol, right? And we have two possibilities for forming the double bond. We have it can go to the left, it can go inside the ring, or it can go outside the ring like what we are trying to make, right? So if it were to go outside the ring, what would be the substitution of that alkene? It would be di-substituted, right? Okay, if it went to the left side, what would the substitution be? I'm gonna highlight it for you guys. 1, 2, 3. So tri-substituted, right? Which one is more stable, tri or di? Tri, right? So are we going to end up making the product that we're given? No, that's the problem. So that's why I would not put the alcohol there. I mean, if you put it, you would maybe get like 2 points off or something. I don't think it would be very much, but that's something that they may pay attention to. So what I would suggest that you do, what is another reagent we can use instead of H2SO4, guys? POCl3. Butoxide, we can use it to make a double bond. It's going to add one extra step for you, okay? Because you have to have an alkyl halide. Then you have to get back to the alcohol anyway, depending on what our starting products can be. But try the other way, and I'll see if it looks good. So basically, let's put your OH right there, okay? And then we're saying instead of H2SO4, which is subject to all this rearrangement, the primary, carbocation, let's put POCl3 instead, and that will ensure that it doesn't undergo an E1 mechanism, okay? Instead, it's E2, and so it allows us to get that terminal alkene there, okay? So that would be perfect to do. That would be perfect. And you can put pyridine. We'll see what she put, but in the reaction section, she typically does put it, but she put it in the synthesis. She put POCl3/pyridine. So I don't know how much that would be off for that. Okay, and then that's the solvent. So then we have this primary alcohol. So what can we do now? We're still trying to get down to a cyclohexane. So we still have to make some carbon-carbon bonds. So what do we need to do? We have an alcohol. You need to right away think what reaction when you see an alcohol. Sorry? Okay, we're trying to form carbon-carbon bonds. That's my hint. We're trying to form a carbon-carbon bond, so we have to use the Grignard. Okay? So with a Grignard here, right away, I'm just going to put then H3O plus on my arrow. Like that, and then I like to make the bigger piece my Grignard, because if you make the bigger piece your Grignard, you're gonna save some steps later down the road. So let's just do that. Let's put MgBr like that, and then what is our other piece gotta be? It's gotta be a carbonyl, right? And particularly what carbonyl? Formaldehyde, right? Because we're only adding one carbon on there. So that's why this formaldehyde has one carbon. So where would this Grignard go and attack? Right there. Push that off. O minus, H3O plus. So that's what we see in our product, okay? How can we form formaldehyde? PCC, because PCC is what type of agent? Oxidizing agent, perfect. So we just make sure that we got a methanol. It has one carbon, just like formaldehyde. Hit it with an oxidizing agent that is weak. Would it be correct to put Jones? Jones would be wrong. That would decompose. So let's see. How do we make a Grignard? You guys know this. Okay. And we must have gone back to what type of molecule? Alkyl halide. All you do is place the magnesium right in the middle between the halogen and the alkyl group. So how do we got to get back to cyclohexane. So how do we add that Br on there? Up or down? Well, the bottom. Oh, you're drawing, right? I will, at the very end, I'm gonna let you guys take your picture or whatever. So what do you have to put, how do you get the Br on there? Br2 and light. What is that word that you gotta write? Perfect, perfect, perfect. You got your 2 points for the excess. Sorry? Excess for the cyclohexane. Yeah, the Br2 is what you're adding, and it's undergoing free radical halogenation to avoid getting like fully brominated cyclohexane ring. So that's the end of our synthesis. Take a picture if you want. How do you guys feel with spectroscopy? Elsa, you're beautiful. I see you. You're like, yeah, I'm tired too. Huh? Alrighty, so let's do the spectroscopy. Let's see what we got. Okay, so compound with the formula C7H14O2. Sorry? Carbonyl right away. So the first thing before we jump the gun, let's just do our unsaturation number, okay? So what's the formula for unsaturation number? 2 times number of carbons plus 2 minus number of hydrogens. Does oxygen make a difference? No, oxygen makes no difference. Then you're going to divide that entire thing by 2, okay? Now, let's solve for it. So everyone take 20 seconds solve for it, okay? 2 times 7, 14, plus 2 is 16, minus 14 is 2, 2 over 2 is 1. Did everyone get 1? You got 1? Did you solve it? So I got 1. Everyone else get 1? Okay, perfect. Okay, Elsa, come on. Okay. So we got our unsaturation of 1. So that could mean either a ring, that could mean 1 double bond. Pretty much it, right? So probably not going to be a ring. Let's go and look what we got. So where do you guys think our fingerprint reagent is going to be in? Either IR? Yeah, I would mark like the 1500 region. Depends on the molecule. 1500 region, cross it all out. Don't worry about it, okay? Then look to see what you got to the left of that, right? And what's really important, I would say, is between that 1500 and the 2000, because that is your double bond region, right? And she loves to put those carbon-carbon double bonds and the carbon-oxygen double bonds. So I'm just going to put that we have a double bond. I would be more inclined to think that it's a carbonyl just because it's near 1700 region, let's just put that we have a double bond, okay? Just not to rule anything out, but I'm leaning towards that it's a carbon to oxygen bond, okay? Just because it's 1700 and it's not super short, but let's see. Then we want to mark our 3000 region. For this particular IR spectrum, it doesn't really matter that much. It doesn't tell us that we have an OH, NH, anything of that much importance. It's just going to tell us we have an sp3 hybridized carbon to hydrogen bonds. They typically like to show up to the right of the 3000 region, right? But all organic molecules are going to have that, right? So we can't use that to distinguish anything, but we can look to the left of it and say we know that those oxygens are now not a part of an alcohol, right? So the absence of that broad OH peak here, the absence of it tells us that we do not have an alcohol for our OA. Those 2 oxygens that are there are not in an alcohol, right? So they could be an ether, they could be an ester, okay? They could be a ketone, but they're not going to be an alcohol, okay? And in our proton NMR, we're not going to see a singlet for an alcohol, okay? So keep that in mind. So we got some double bond, which is perfect because our unsaturation is 1. So that's good. Now let's make our way to the proton NMR. And what I like to do is make my way from right to left and figure out, what pieces are present. And then we'll focus on how they're connected, okay? So integration number of 3 is going to tell us we have a CH3, right? What do you guys think about an integration number of 6H? Are we going to have a CH6 or something? No, right? So what do you think? Perfect. So we'll put 2 CH3s, right? This is a ratio that they're giving us. So you're not going to have a carbon with 6 hydrogens. Instead, you could have 2 methyl groups. Find the simplest division, right? So the 2 methyl groups of the 3 protons on each would account for same environment methyl groups. So that's really important. Then let's make our way to the next thing. What do you guys see at that 2H? What does that mean? Probably CH2. So I'm going to box it. And then move our on long, so CH2. Okay, then we move all the way. There's even a split in the graph to show us we're moving over to the 5.0 region. Okay, so that's incredibly downfield. That stands out to me. And then, so that could be a CH. Okay, for the OH peaks, they're not gonna have splits here. Okay, you're gonna see them always show up as singlets, and we already deciphered that there's no OH. So now what I like to do, just to avoid making any more mistakes later on, count the number of carbons and even hydrogens if you want, in order to confirm that you got the correct number that on your paper. So let's go back to our molecular formula and count it out, okay? So right here, we are supposed to have 7 carbons, right? So let's go and check in our boxes. So we have 1, 2, 3, 4, 5, 6. Uh-oh. What does that mean? For some reason, we're missing one. So if we're missing one, then that means that we must have a carbon that does not have a proton on it. And that's the reason why you're not seeing that proton signal in the proton NMR. Could it be that it's what? Yes, you're on the right track. So that could be a part of the carbonyl, right? And so now we're accounting for one of the oxygens. We have to make sure, let's put the other oxygen, because I think one oxygen is 4 points, like, my gosh. So we'll put the other oxygen. So 1, 2, we got those down. We got the number of hydrogens and we got the number of carbons, okay? So does that make sense, how I figured out that that was a carbonyl? And that explains the 1700 region and the unsaturation. Okay, so now let's make our way back. Let's make our way back to that CH3. And what does that first CH3 have to be attached to? Something that has 2 protons. And here we have 2 CH2s. So it's going to be one of those guys. So I'm going to look at both of them and figure out which one has more splits. Okay? So that would be, of course, the one that's towards the right. Okay? So I'm leaning towards that one's probably going to be connected there. Okay? And we'll check as we go. Then let's look at our 2 CH3s, the ones that are giving the integration number of 6H. And what is our splitting pattern? We see a doublet. So they have to be connected to what? A carbon that has how many protons? 1. And how many carbons do we have that only have 1 proton? 1. So they both have to be connected to the CH, and that's what's allowing them to be in the same environment. That's why they're being detected as the same, because they're both detected to the same CH, which will then be detected to the same stuff. Okay? So now let's make our way over to the other CH2, right? And what's the splitting pattern of that guy? It's a triplet, right? So what does that have to be attached to? A CH2. So there's only one other CH2, so let's connect it to that CH2. But from the other side, right, can it be connected to another carbon that has protons? Let's look at the splitting again. So we have 1, 2, 3. So the n+1 rule told us that we are connected to a CH2, and from the other side, we cannot be connected to anything that has protons. Okay? Yeah, you're on the right track. So then let's check out our CH. How come that CH is all the way at the 5.0 region? It's downfield. And the reason for that is because it's directly attached to a very electronegative atom, which the only one we got here is the oxygen. So that means that CH has to be directly attached to the oxygen. Okay, so let's put that. And even comparing the splitting pattern of that CH, look at how many splits we see. That could be due to the 2 methyl groups. So theoretically, we should be seeing, if there's the 2 methyl groups of same environment, we should be seeing 3 plus 3 plus 1, right? And that's 7. So let's see if it's theoretically correct. Yeah, so it happens to be a really good spectrum. So it gives us the 7 that we're looking for, right? And then what else do we have left? So we really have only one option of like how we can take this, right? That one of the CH2s is a little bit more downfield than the other one, right? So that could indicate that that one is the one that's directly attached to the carbonyl, which has an oxygen, but that's why it's not as downfield as the CH. And then this could connect to the oxygen to give you the ester. And if you want just a little like hack, if you're trying to figure out if this is a ketone or an ester, that carbonyl carbon, go down to the, I would say never use the carbon 13, but for this, go back and check. If you see a signal at around 180, that's for the carbon of an ester. So that's how, right, like when I was looking at it at the beginning, I creeped down there, I saw that 180, and I was like, okay, we're gonna have an ester. You see, so that's a little trick for you guys. I didn't learn that till after I took orgo. So that sucks. So now let's go and write everything that we have in our box. So we're gonna have CH directly attached to a CH2, directly attached to another CH2. It's gonna be directly attached to the carbonyl. It's gonna be directly attached to the oxygen. It's gonna be to the CH, and of course that CH is gonna have the two similar environment methyl groups, and that's how we're gonna end it. Let's check. Drum roll. Oh my God, it's right. It's right, you guys. So that would be your answer. All right, do you guys have any like general questions? No? Okay, perfect. Thank you guys so much for coming. I apologize for the technical difficulties, but thank you so much, and best of luck for your exam, okay? Yes, sir. Anything for my Nook girls. What's up?
So for this one, I was asking about the multiplicity of
Oh,
CD.
wait 1 second.